Um, Under 9.3, you can transform any normal distribution into Z and use tables. And of course, up there, page 182, a normal distribution can be used to model a number of different variables. Or you could have you could have one that looks like this, and this one is the mean is there, and the whole of this thing is a function of x. And you can see we have a large, this is where we have a large value of the standard deviation. You could have a different one that has a sharp peak. That is it's the same thing, the function of x, and this is a small value. This one shows a small value of the standard deviation. You can see from here to here is larger than from there to there. But anyway, the distribution will have the same familiar bell shape, but the mean mu and the standard deviation will be different. Some 3 points to note before we go to example 3. The random variable x having a mean of mu and a standard deviation, or variance, when this is the standard deviation, that follows that the variance is the square of the standard deviation. That is it. Can be written as x is distributed normally between a mean and the variance. Now, this can be transformed into the random variable z. And the x is any number. You can be given any number from any data. And this one can be transformed to z. And that's how we're going to learn. That's how we are here to learn. No, 0, all the way from 0 to 1, which is a general distribution when the mean is 0 and the standard deviation is 1. This one happens by the formula z is equals to x minus the mean all over the standard deviation. All over the standard deviation. And because all these are estimates, then you can round off your number into 2 significant figures so that you can get numbers which you are interested in the table. Remember, the table represents z, or the table displays z, not x. And that is why we would wish to convert every kind of x into z. And this one is going to be seen in example 3. So let us straight go to example 3, and we are being told that having understood that, let us try to go through example 3. The random variable x is distributed normally the mean of 50 and the standard deviation of 4. That means the variance is 4 squared, which is 16. Find the probability of x less than 53. And this one is now, because we do not have the z, we don't have the z here. It is asked to create the z using the formula which you've just understood. Z is equals to x minus the mean over mu. And in this case, our z is going to be given by, 53 minus 50 over 4. And this is something to do with, this is 3 over 4, 0.75. So our probability, now that we have z, is going to be Z less than 0.75. And of course, we go direct now to the table and we find the boundary, which is talking about 0.75, page 201, 0.75, and the area is 0.7, the area is 0.7777734, and that is it. Because, well, you may present this information using the model, and you may have, of course, our mean is 50, so our 53 is to the right of 50, and we want the area of this shaded region. So when we are talking about 0.7734, it makes a lot of sense because you can already see it's more than half. Part B, the probability of x less than 45. Less than 45. And this one is just, we can rewrite it in the following format: the probability of z less than 45 minus 50 over, you divide by 4, which is the standard deviation. And this one is simply, if you talk about 45 minus 50, is negative 5 over 4 is negative 1.25. So this, the whole of this arrangement becomes z less than negative 1.25. And this one, it's simply represented by a model that looks like this. Negative is to the left, negative 1.25. And because it's less than, then we are looking for that particular region. Let's call it region A. And this is what, when we say it symmetrically, because we don't have z values which are negative, symmetrically we have 1.25 across, and this is the area again. We can also call it A because they are equal. So practically we're looking for the probability of z greater than 1.25. And this one is just a matter of 1 minus, because we don't have, on page 201, we don't have the value of z greater than, we only have the value of z less than. So we know this is 1 minus because we need to get the area of this region, so we have to have the whole area of the model minus this. So meaning minus the area when the boundary is 1.25 less than. So the probability of z less than 1.25. And all we need to go now, we need to go to the table, page 201, and we find that when the boundary is 1.25, what is the probability? And we find it 0.8944. So the probability of z less than minus 1.25 is equals to 1 minus 0.8944. And this one is simply 0.1056. 0.1056. A great care should be taken when we are using this, because sometimes they'll give you negatives, but that is not a problem. When they give you negatives, we have learned how to deal with negatives. If we have negatives, then we go to the greater than. If the greater than can actually be solved by consulting the table on page 202, that is the percentage table, then so be it. But if it is not, then you go to 1 minus the region that is greater than. That is as far as example 3 is concerned. Please take note and use this information in your exercises. All right.